Can we begin the session now? Is it okay? Professor Bufetov, can we begin the session now?
Yes, of course. Yes.
Yeah. So, hello everyone. Today's plenary speaker is Professor Alexander Bufetov, and the chair for the session is Professor M.T. Nair. So, can you please come on stage and introduce the speaker?
Good afternoon, everybody. So, welcome to the first plenary talk in the afternoon of first day of the conference. The speaker is Professor Alexander Igorovich Bufetov from Steklov Institute of Mathematics, Russia. He will be speaking on determinantal point processes, Gaussian symmetries, and interpolation. Professor Bufetov.
Okay, thank you very much for the kind invitation. It's great pleasure for me to speak at this conference and even virtually to be with you in India, the country of Varahamira and Bhaskara. So let me start. Let me start with the standard example of determinantal point process. So I start with the sine process. I consider the sine kernel. So please let me know, because I just a moment ago I saw the blackboard, but now I actually see the room. So it's nice to see the room, but please let me know if you have any difficulty to see the blackboard, and I can write bigger. And also, please do not hesitate to ask questions, because in fact, I can see you very well. Please don't hesitate to interrupt me at any moment. Okay, so I consider the sine kernel, which is written here. So this is the kernel on the real line. It's a kernel that acts in L2 of the real line, and in fact projects L2 of the real line onto the Pelley-Wiener space. So where, let us recall that the Pelley-Wiener space is the space of functions in L2 whose Fourier transform has support in minus pi. There we go. So this is just this projection. To this projection corresponds determinantal point process, the sine process. The sine process. So the easiest way of seeing the sine process is a scaling limit of random unitary matrices. Let me skip the formal definition for the moment. I will recall it later. Let me just say for the time being, yes, question? Okay, let me just say for the time being that the sine process is process on a point process, so a probability distribution on the space of configurations on the real line. That is to say, on the space of infinite subsets of the real line without accumulation points. So while I hear some noises corresponding probably to chat, while I do encourage everybody to ask questions, I ask please not to use the chat, because I cannot see the chat. So if you ask questions, please ask me directly. Okay, so, and please do not hesitate to ask questions just in voice. This sine process, which is a measure on configurations on the real line, infinite subsets of the real line without accumulation points. So there is a question naturally arises about the connection between realizations of the sine process, that is to say, configurations of the real line, and the Pelley-Wiener space. And the first result in this direction belongs to Subrosekar-Ghosh, who proved that for almost any realization of the Sine process, almost every realization of the Sine process is a uniqueness set for the Pele-Wiener space. Is a uniqueness set for the Pele-Wiener space. What does it mean, uniqueness set? Is a uniqueness set for Pele-Wiener space. What does it mean, uniqueness set? A function in the Pele-Wiener space is an entire function. Is an entire function. So this entire function has some zeros. There cannot be too many. In fact, zeros of a Pele-Wiener function is a classical, well-studied subject. There cannot be too many. So a subset of the real line is a zero set for the Pele-Wiener function if there exists a Pele-Wiener function which assumes value 0 at all these points. So, for example, integers without 0 yields, considering integers and removing 0, yields a 0 set for the Pele-Wiener space, because the function sin x over x is indeed a function which is 0 at all integers except 0. A uniqueness set, on the other hand, is such a set, a restriction to which determines a Pele-Wiener function uniquely. And here we can recall the classical theorem of Kotelnikov from 1933, Kotelnikov 1933, that a Pele-Wiener function is in fact recovered from its values in the integers, in all integers. I write x minus k, of course, sine pi x minus k is equal to sine pi x, but I write this x minus k just to stress that these are shifts of the sine kernel. These are, in fact, reproducing the kernels, shifts of the reproducing kernel. So the theorem of Kotelnikov gives, in fact, orthogonal representation for the Pele-Wiener function. Gives a representation for a Pele-Wiener function as an orthonormal series with these coefficients. This is a quite special property of the set Z. Okay, so the set Z is a uniqueness set for the Pele-Wiener space, because in fact, as Kotelnikov's theorem shows, the function f is uniquely determined by its values in the integers. Here is the representation, and on the other hand, Z without 0 is Z without 0 is a 0 set for Pele-Wiener space, in that the function sine x over x, sine pi x over pi x is in fact 0 at all integers except 0. This also one can see from the Kotelnikov theorem, that the representation here is complete and minimal. The set Z is a uniqueness set for Pele-Wiener space, but at the same time, removing even one point yields a 0 set for the Pele-Wiener space. Okay, so after this, I'm ready to formulate the main result of this talk, which is a complement to the theorem of Subrosekar-Ghosh, and which says that, so this is the main result, that it's on the archive. So from 2019, so that just almost every realization of the Sine process, minus one particle, and this is the key point, minus one particle, is a complete and minimal set for the Pele-Wiener space. Is a complete and minimal set for Pele-Wiener space.
You wanted us to ask question.
Uh,
Yeah, one question.
Excuse me, sir, there's one question.
Can you hear?
yes, I can hear you. Yes.
So this f is a perimeter function. What is the point-wise evaluation f of k? Because
Yes.
there are two functions, right?
No, there's only one function f here.
No, the
F is
right.
a perimeter function.
Yeah, fx is determined by values of f at k.
That's exactly right. Where summation takes place over all k in Z.
So are they meaningful in the sense they are two functions, right? In the sense,
Why two? Only one function f.
correct.
You see the blackboard clearly? There's only one Peleviner function f.
Yeah, they are L2 function, that is square integrable functions.
But this is what I said. No, thank you very much. This is what I said, but maybe not clearly enough. While it is, thank you very much for your question. While it is indeed an L2 function from the fact, thank you very much for your question, it's quite important actually to understand this very clearly. Since the support of the Fourier transform is in a compact interval, it is in fact entire function. So in fact, evaluation, no, but this is very important. This is very important. Evaluation functional, so this will be general setup also in other examples. Thank you very much for stressing this point. In fact, the reproducing kernel, which is written here, so this is an L2 function. So evaluation functional is in fact just inner product with this function. So value. So this is a function of two variables, and I can write that.
Well, that's a reproducing kernel.
Is equal to the inner product of S x naught dot with F. So you can see, and also again, it's much more general. You can see that the value of a function is a result of taking the inner product of the function with the reproducing kernel. So in fact, it is well defined at all points. And again, in this specific case, we're dealing with entire functions. But in some other examples, these are not entire functions. But this equation will make sense always. All the spaces that we will consider will be spaces with reproducing kernels. And results of this type also make sense much more generally. Thank you very much for your question. Okay, does it make sense now?
Yes.
Good, thank you very much. Okay, so I continue. So sine process minus one particle is a complete and minimal set for the Peleviner space. Let me underline that in contrast to what one might think, having a uniqueness set, which Gaussian guarantees us for the sine process, having a uniqueness set does not guarantee existence of a minimal subset of this uniqueness set. This is not guaranteed. And let me give a second example where the situation will be quite different. So before I formulate my second example, let me just say, that in this first example, we also will obtain analog of theorem of Kotelnikov. It will be joint work with Bufetov and Klimenko. I will formulate it a little bit later. So let me now go to a second example. This will be example related to Gaussian analytic functions. Okay. So I consider the unit disk, which in fact it will be convenient to consider as Lobachevsky plane. So I consider the unit disk. So, and I consider a random power series, sum an Zn, n from 0 to infinity, where an's are independent complex Gaussians. And then I consider zero set of this random power series, zero set X. So zero set X, in fact, since these are independent complex Gaussians, it is one verifies without difficulty that the radius of convergence of the series is equal to 1. So the zero set is in fact a configuration in the open disk, accumulating only at the boundary, It is beautiful and important that the law of the zero set is invariant under the Lobachevsky anisometry. So viewing this disk as the Lobachevsky plane, Lobachevsky anisometries act on it, and the law of the zero set is invariant under Lobachevsky anisometries, whereas the law of the power series, in fact, is not. So, in fact, it follows from a beautiful, what I just said, follows from a very beautiful theorem of Perez and Verhaeghe from 2003, that the law, the correlation functions of this zero set, so the infinitesimal intensities of this zero set, are given by the determinants of the Bergman kernel, where the Bergman kernel is in fact, so here again we see a situation somewhat similar to what we saw before. So the Bergman kernel is the kernel of orthogonal projection from L2 to, so L2 considered to the usual Euclidean Lebesgue measure, L2 of the disk onto the space of holomorphic functions on the disk. So this is the Bergman space of holomorphic L2 functions. So monomials in the space of holomorphic L2 functions, monomials form an orthogonal basis. Their inner products are computed without difficulties, and Y arrives at the formula for the Bergman kernel. There exist several proofs of the Perez-Verhaeghe theorem. My favorite proof is the proof by Manjunath-Krishnapur, where Krishnapur just connects the zeros of the Gaussian analytic function to the eigenvalues of a random unitary matrix. This might seem completely impossible because the eigenvalues of a random unitary matrix belong to the unit circle rather than to the unit disk. But in fact, Krishnapur cuts out a corner from a random unitary matrix. So, and for a corner of a unitary matrix, in fact, eigenvalues belong to the unit disk. And if a corner is cut in a certain smart way, then one arrives at the Perez-Verhaeghe theorem. Okay, so just the question again arises, and for the analog of the theorem of Gauche in this setup, and this is in fact obtained in joint work with Yang Xiu from Chinese Academy of Sciences and Alexander Shamov and CNRS and Alexander Shamov from the Weizmann Institute in Israel. So just in joint work, we show that almost every zero set, almost every X, is a uniqueness set, for the space A2. So let me point out that, of course, this function is almost surely not square integrable. This function is almost surely not square integrable. In fact, this function one can compute the variance and one arrives at the harmonic series, because the variance of z to the n is 1 over n, the variance of an is 1. So one arrives at the harmonic series, and the harmonic series, so the divergence of the harmonic series by the Kolmogorov two-series theorem implies that this function is not square integrable. At the same time, it could be possible to imagine a function which has the same zeros, but maybe with some exponential factor or something else, with some, the set of zeros does not determine a function uniquely. Maybe some modification of this function, which would in fact be square integrable. So our result with Xu and Chanov shows precisely, so this is 2016, shows precisely that this is not possible. This is not possible. So, and let me just say that the setting here is quite different. This is precisely what I wanted to emphasize. The setting here is quite different from the setting in the previous theorem, in that this uniqueness set, so this is uniqueness set for the Bergman space. Any Bergman function is uniquely determined. Any Bergman function is uniquely determined by its restriction onto this set. But this set not only is not itself minimal, but in fact, it cannot possibly contain a minimal subset. It cannot possibly contain a minimal subset. So we are used to the fact that the basis, well, if, for example, a spanning set in vector space contains a subset which is a basis. But here we are dealing with infinite sets, which are very far from being a basis. They are not a Riesz basis. I can explain why not separately. In fact, it is not possible to find a minimal subset. And in fact, it's quite clear why. It's very simple to explain why, because in fact, removing or adding, for that matter, removing or adding any sequence of points, maybe even infinite sequence of points with convergent Blaschke product doesn't change uniqueness property. In particular, adding or removing finite and many points doesn't change the uniqueness property. Because in fact, so let us recall, what does it mean, uniqueness property? Uniqueness property means that if f is a square integrable holomorphic function, and f in restriction to x is equal to 0, then f is identically equal to 0. But observe that just multiplication by z is bounded operator in this space. So if f is equal to 0 at all points except finitely many, then one can multiply f by a polynomial and obtain a Bergman function which is 0 also at remaining points. And similarly, even for infinite sequences with convergent Blaschke product. So in fact, I'm just trying to say that this subset does not admit any, this uniqueness set does not admit any minimal subset. So the question arises, how to interpolate? So we know that a Bergman function is uniquely determined by its restriction onto this set. But how to get it from there? So this is joint work with Xu, so 2018-2021. So in fact, so how to interpolate? How to interpolate? The question is how to interpolate. How to interpolate f from f in restriction to x. So so joint work with Xu, 2018-2015. So just the interpolation, as this reasoning shows, must not depend on the function f inside the disk. It can only depend on the boundary. At the same time, Bergman function does not have boundary values. So a Hardy function has boundary values. So if we were dealing with Hardy function, there would have been nothing easier because a Hardy function admits boundary values. So I just compute the values at the boundary by taking the limit, and then I interpolate. But such situation is not possible. There are no boundary values. At the same time, and this is precisely the result of joint work with you, these boundary values exist in some weak sense on average, and precisely the Patterson-Sullivan construction yields the desired interpolation. That is to say, so I want to recover my function at some point z0, and I write f of z0 is equal to the limit as s goes to 1, and then I write precisely the Patterson-Sullivan series, sum e to the minus s distance from z0 to x f of x, sum e to the minus s distance from z0 to x. So distance here is Lobachevskian distance. Distance is Lobachevskian. So this is the reconstruction. The point which cost us a lot of effort is that this reconstruction is not uniform in F. It is not uniform in F. So it is uniform in Z0, but not in F. Such reconstruction, it is not possible to have it for all Bergman F simultaneously. And we prove in the paper, it's on the archive also, we prove in the paper that it is not possible to have such reconstruction uniformly for all F in Bergman space. So in fact, if similar formula is written, but instead of F values f of x, I substitute reproducing kernels, then we have a lower estimate on the L2 norm of such additive function. So informally, the reason is that, well, when such a formula is written, there is a set of measures 0 which is being thrown away because I'm considering a random set. So there are some random sets for which the series diverges. It's a set of measures 0. This is what we prove. But this set of measures 0 depends on F. This set of measures 0 depends on F. So it depends on F in a very strong way. We only prove that such formula holds uniformly in some relatively small subspaces of the Bergman space. So some subspaces which go beyond the Hardy class, but still are relatively small subspaces of the Bergman space. Let me also say very briefly that this construction and this reasoning applies essentially with technical changes to setup of several complex variables. So here I consider the case of determinate point process with Bergman kernel in disk, but it's also possible to consider, for example, ball in several complex dimensions. Okay, so after I have explained this Patterson-Sullivan construction of joint work with Yang Zhu from Chinese Academy of Sciences and CNRS, so just let me now go back to the sine process. So interpolation for the sine process. So interpolation for the sine process, and interpolation for the sine process will be quite different. So let me again, so we go back to the sine process. Let me again formulate interpolation for the sine process. So let me again formulate the main result. So of the talk that almost every realization minus one particle is a completed minimal set. Minus one particle. One particle is a completed minimal set for the Pellinger space. Complete minimal set. Space. And let me contrast this result with the situation for finite and many particles. In fact, let us recall that Sine process arises as scaling limit of eigenvalues of random unitary matrix. So let us consider just random unitary matrix into the hard measure. So we recall that study of random matrices goes back to the work of Ronald Fisher and was then continued by John Wishart and just Wigner and Dyson. So let us observe that for the zeros of random unitary matrix distributed according to hard measure, correlation function of the zeros that can be computed explicitly, and it becomes the Dirichlet kernel, the determinant of Dirichlet kernel. Determinant of Dirichlet kernel. This determinant comes from the Weyl character formula, and this is where the determinants, all the determinants that I'm writing today come from the Weyl character. So let me write theta I minus theta j. Okay. So this is the correlation function of the eigenvalues of random unitary matrix. This kernel, the Dirichlet kernel, is of course the kernel of a projection. It's kernel of projection on the first n Fourier frequencies. I take Fourier series, just Fourier series, and I cut the first n frequencies. So first n frequencies including the zeroth frequency. So it is clear that polynomial, trigonometric polynomial of degree n is uniquely determined by its n values. So I have n particles, n eigenvalues, n particles. I have my kernel of projection onto the space of trigonometric polynomials of degree n. It's clear that if polynomial of degree n has n zeros, there is something I'm not saying right. So polynomial, if polynomial of degree n minus 1, if polynomial of degree n minus 1, because I'm considering n frequencies including the free term. So if a polynomial of degree n minus 1 has n zeros, then this polynomial is itself 0. Polynomial of degree n minus 1, so is uniquely determined by its n values. Now we take the scaling limit. So the scaling limit taken by Dyson. So Dyson observes that the distance between neighboring eigenvalues is on the order of 1 over n. So it makes sense to take scaling limit. So scale, expand. It's not 1 over n, it's in fact 2 pi over n. So expand by n over 2 pi. And in the limit, precisely obtain the Sine kernel. So the determinant becomes the determinant, and the kernel, let me erase this determinant. Well, let me put it in brackets. Determinant, here's determinant. Of course, determinant goes to determinant, but the important thing is that the Dirichlet kernel converges to the Sine kernel. In fact, the n harmonics under scaling converge to Pelly-Wiener space. This statement can be made completely precise. So it is a very clear image that I have these n harmonics which I scale, and they converge to continuous spectrum. Here we go. So, but just the kernel converges to the Sine kernel. So the fact that the configuration is still uniqueness set, the theorem of Gaussian, is in fact preserved by limit transition. But the nuance is that the fact here for finitely many particles, this is zero set, uniqueness set, but it's also minimal set. Even if I remove only one particle, then it is no longer a uniqueness set. And this fact, minimality, is in fact destroyed by the limit transition. The limit transition does not preserve the minimality. In fact, there is one more particle that one needs to remove here in order to obtain completed minimal set. So I aim to explain where this -1 particle comes from in the final part of the talk. But before I do this, let me first say that, well, a polynomial or trigonometric polynomial, to recover a polynomial from n values, there is Lagrange interpolation formula. So in fact, we prove in joint work with Borichev and Klimenko that there is Borichev from Marseille and Klimenko from the Sekov Institute in Moscow. So we prove in joint work that in fact Lagrange interpolation also works for the Sine process, for almost every realization of the Sine process. But we have an extra assumption. So in comparison with the Kotelnikov theorem, so Kotelnikov theorem is precise. It gives representation of any Pelley-Wiener function as sum of a convergent series with orthogonal terms. So our Lagrange interpolation, the terms will of course not be orthogonal. They will not in fact form a Riesz basis. So they will not be orthogonal, and they will not be deformation of orthonormal basis by automorphisms. This is just not true. So provided, so we need to say provided, this is important, f decays sufficiently fast at infinity. So let's say f times 1 plus t squared to the power n is in L infinity. So provided, and we just claim that there exists such a knot. We don't aim to find optimal value. It seems likely that it should be possible to take a knot something like 3 or maybe even 2, but we don't pursue this in this paper. I think it would be very interesting to find optimal value, but we don't. So we only say that if f decays at infinity sufficiently fast, then Lagrange interpolation formula also works. And this is joint result with Borichev and Klimenko. Okay, so what exactly do I mean? Now I'm ready to go to the final part of the talk and to give a few proofs. How much time do I have? Just to make to be sure that we're on the same page on this.
So there's about 7 minutes left.
Yes, that's also what I thought. Okay, good, perfect. So in the remaining 10 minutes, let me say how in a vague outline of the proof of this result. It's on the archive, so all the details are there on the archive. But let me just give an outline. So once one says the Lagrange interpolation formula, so how does one start with the Lagrange interpolation formula? Again, here I have trigonometric polynomials, but let me forget about this. I will now discuss usual polynomials. So how do I start with Lagrange interpolation formula? The first step in Lagrange interpolation is to form a polynomial which is 0 at all points from which I do Lagrange interpolation. So, and this is precisely what I now do here, except it will not be a polynomial. It will be a random entire function random entire function. So x is the configuration of the side process. So x is the scaling limit of eigenvalues of a random unitary matrix under scaling, which is written here. So t is a formal variable. So, and I consider the following random entire function. The product is taken over all particles in X. Please observe that the product only converges in principal value. But the product does converge in principal value. For example, if I were to take X to be integers, then the function would be the sine function. So just to give an example. But in fact, this is the whole point. This -1 particle is precisely obtained because this function, being a random function, in fact is not a bounded function, but in fact has growth. Okay, let me explain these points more precisely. So the statement of the theorem is in fact equivalent. I will not explain why, I will only very briefly say why it is equivalent. The statement of the theorem is equivalent, so I say reformulation, to the following statement, that if PQ in X, then first step, gxt over t minus p does not belong in L2. And second claim, Q are first different. So gx of t divided by t minus p does belong not only in L2 but also to the Peri-Wiener space. So this is the claim. So let me point out that Peri-Wiener space is a de Branch space and in fact satisfies axiom of division. So just like polynomials. So obviously if I have a polynomial and the polynomial has a root, then dividing by t minus the root, I obtain again a polynomial. Similarly, if I have a Peri-Wiener function, which is 0 at some point, then dividing by t minus this point, I still obtain Peri-Wiener function. Furthermore, if a Peri-Wiener function is such that t, the variables, times the Peri-Wiener function belongs in L2, then in fact it also belongs to Peri-Wiener space. So these properties hold in much greater generality, and in fact, the statement 2, the claim 2, also holds in significant generality for so-called processes with integrable kernels, or equivalently, as we show in joint work with Romanov, equivalently processes which satisfy the division axiom. The division axiom that we need with Romanov is weaker than the branch axiom, because the branch axiom, there are some other properties which we don't need. We only need the property of division. And in fact, we obtain a somewhat larger class of examples than the branch space. Okay, but in any event, so these are the claims that I need to prove, and the key claim is this one. The key claim is this one. So it is convenient to shift my x a little bit. So to consider not x, but x plus IA, like this. So to shift, for a reason that will become clear in a moment. The statement is the same, and the proof, so the two statements are equivalent. The two statements are equivalent. But this one will be more convenient for a reason that will become apparent in a moment. So this is a product. Taking the logarithm of the product, one gets a sum. Taking the logarithm of a product, one gets a sum. So the first main step in the proof of this result is a detailed understanding of additive functionals for the sine process. So I consider additive functional for the sine process. And I would like to know how this quantity behaves. So the answer to this question is given by theorem of Séguin in the form of Borodino-Konkov-Geronimo case, of which we take scaling limit of theorem of Borodino-Konkov-Geronimo case, which is a version of theorem of Séguin. Theorem of Séguin has very beautiful history. Séguin started working on his theorem in 1915 when he was 19 years old and was in the trenches of the First World War. He completed the work on his theorem in the 1950s when he was already a world-famous professor in Stanford and the Second World War was already over. And so his result on asymptotic of Toplin's determinant is, well, justly famous and is source of always new inspiration. But unfortunately, one cannot take scaling limit directly for the theorem of Séguin. One cannot take the scaling limit directly. It is possible, however, to take scaling limit in the theorem of Séguin in the form of Borodino-Konkov-Geronimo case. So where Borodino-Konkov-Geronimo case, they do theorem of Séguin with error term, So, and let me write scaling limit of the result of Borodino-Konkov-Geronimo case. So I take the expectation of the exponential of the additive function. So in fact, the key point is that this expectation can be estimated quite precisely. So first, there is, of course, lambda times the expectation, this is clear, lambda times the integral factor. Then there is the term of the second Séguin theorem, so which is 1/2 square root lambda square Sobolev 1/2 semi-norm. Sobolev 1/2 semi-norm. So let us recall very briefly that just Sobolev 1/2 semi-norm Sobolev 1/2 semi-norm is the double integral f of x minus f of y. Y, which is the same as the integral absolute value of lambda Fourier transform of lambda square d lambda. So Sobolev 1/2 semi-norm in particular is invariant under scaling of the line. Okay, so here is Sobolev 1/2 semi-norm. And then there is also error term, which is the key point. Let me write it, I will write it in somewhat enigmatic form. Let me refer to the preprint for the details. It has the form of 1 minus a certain Fredholm determinant, which, please allow me, for lack of time, not to write more precisely. But there is a certain Fredholm determinant, which it is possible to estimate with great precision in some situations. So, and in particular, this expectation of multiplicative functional, it is essentially normal. It is essentially normal. And therefore, this quantity, the logarithm, the exponential of this normal value, it is normal, and the variance, by the way, it is now clear why I have this IA, because this IA precisely allows me to get into the Sobolev 1/2 space. Otherwise, for A equals 0, it does not belong there. Variance is logarithm of t. And precisely because random variables sometimes have large explosions, this function fails to be in L2, because sometimes this function is just bounded. And let me just say very, very briefly in the remaining minus 1 minute that I have, that just the key technical step in carrying out this scheme just is the step of evaluating high frequencies of this quantity, because it is necessary to evaluate this probability of large deviations. And in order to evaluate high frequency, what is necessary is the statement that the analog of definite theory for sine process, the statement that the sine process, it is of course not invariant under diffeomorphisms of the line, otherwise it would be Poisson process, but it is quasi-invariant under diffeomorphisms of the line. So the sine process acted by diffeomorphism with complex support, diffeo with complex support, and this is a theorem from 2014. So just is in fact quasi-invariant under the action of the group of diffeomorphisms with complex support, and the Radon-Nikodym derivative is computed explicitly as multiplicative functional over pairs of particles, so it's computed quite explicitly. This action, quasi-invariance under action of the group of diffeomorphisms, allows one to use change of variable in the spirit of Johansson, and for large imaginary lambda, change contour of integration and prove decay of these frequencies, which in turn allows one to prove using Bailey-Zimond inequality and approximation by hierarchical random variables in the spirit of Kissler and Jan-Belus-Bourgade, that these quantities sometimes become quite big, sometimes become quite large, and so that this function is not in fact in L2, which gives the proof of the main result. Thank you so very much.
Any question from the audience, offline and online? I have one more query. Is it on?
Yes.
Yes.
Yeah, I have one more query here. Hello?
Yes, yes.
Yeah, so you talked about this interpolation.
Yes.
F at Z naught is the limit s tends to 1 of some expression involving x.
Yes.
So that is independent of which x you choose, or any x you choose?
No, x. So excuse me, you mean Patterson-Sullivan interpolation?
Yeah.
So in the formula that I wrote, Z naught. So let me write the formula again, just a moment. So the formula in the formula that I wrote. So Z naught Z naught is any point in the disk. So I take limit as s goes to 1. Then the summation is over all. So actually s d z naught x over all x in the configuration, and maybe so the zero set. So maybe I didn't say clearly enough that summation needs to take place also in principal value, namely over annuli. So over annuli, there are heavy compensations. This is the whole point. Because of course the sum does not converge in absolute value, and then there is normalization. So summation is over all particles in my configuration. Please observe, it's very important, over annuli, so convergence takes place in principal value. Does it make sense?
Yeah, right. Another point, you talked about the Bergman kernel and the eigenvalues within the unit disk, right? And,
yes.
So these eigenvalues associated with the operator corresponds to the Bergman kernel, or? Can
you ask the question again, please? These eigenvalues are what?
Yeah, you talked about the eigenvalues within the unit disk and the Bergman kernel. Yeah, the Yeah, so is it associated with the operator associated with the Bergman kernel? The eigenvalues of the operator associated with the Bergman kernel?
The Bergman kernel
Yeah.
is kernel of project. You say, is it possible to realize Bergman kernel as spectral projections? This is the question.
Yeah. So the eigenvalues are associated with the operator corresponds to the Bergman kernel? No, not necessarily.
So I don't know. Is it possible to associate? I don't know of such result.
Okay.
There are many experts in the audience.
I thought the Bergman kernel will give a corresponding, positive definite operator, right? You have the integral operator.
Let us just to avoid confusion. So Bergman kernel is of course kernel of projection onto Bergman space. So Bergman space is space of integrable square, integrable holomorphic functions. On the other hand, with Pelley-Wiener space, there is, so to speak, in the background, there is a differential operator of taking second derivative, of which Pelley-Wiener is spectral projection. Is it possible to have some natural non-self-adjoint differential operator? This I understand to be a question for which the Bergman kernel would be spectral projection. I do not know.
Okay. Anyway, so I
do not see
connection between the eigenvalues and the corresponding operator. Fine. Yeah. The Bergman kernel will have an operator, and that will give a positive definite operator, integral operator also.
Bergman kernel, of course, is a positive definite integral operator. It is operator. This is clear. Of course, it is operator of projection on subspace. It's Hermitian projection operator. Yes.
Okay.
Yes, of course.
Whether the eigenvalues are associated with that operator, that's not my question. Yeah. Eigenvalues within the unit disk, which you talked about.
So precisely, no, I understand the question, and my answer is I don't know.
Yeah.
So precisely, I don't know of any.
Yeah.
Precisely, I don't know. So is it possible, as you say?
Yeah.
So if I take random unitary matrix and I consider I consider the limit, then the limit is Pelley-Wiener kernel, which is spectral projection. Is it possible to have the Sine kernel is projection onto the spectrum of self-adjoint operator? Well, if you wish, one-dimensional Laplace. So is it possible to have natural operator for which would be natural spectral projection operator corresponding? So Bergman kernel projects upon monomials, projects upon 1 z squared z to the k, but I don't see any natural corresponding operator. Maybe I don't see such counterpart, such natural counterpart.
Okay, so if any question again? So if there is no question, let us thank Professor Bufetov once again for an interesting talk.
Thank you very much. Thank you.